Hi everyone, in this video we are going to talk about how we can tackle precipitation questions. So as I've mentioned in the previous video on dissolution questions, we need to first look at a question to decide if it is a dissolution question or whether it's a precipitation question. Once you realize there is a precipitation question, you can straight away use this simple concept. So the concept that we are looking at this point in time is the idea of IP versus KSP, which is very similar to what we have seen in the chapter of chemical equilibrium, where we considered the reaction quotient Q versus K. Their only difference is that K is at equilibrium and Q is at any point in time. So momentarily, what is at that what are the concentrations present, and that is how we calculate them out. So for precipitation, there are a couple of cases. Basically, to draw a parallel, okay, let's do a quick review on our Q versus K. So there are only three instances. Q can be greater than K, Q can be smaller than K, Q can be equals to K. So when Q is equal to K, we are at equilibrium and the system will want to travel from Q is larger than K to Q is equal to K, or Q is smaller than K to Q is equal to K. So what will happen is that if Q is smaller than K, it would want to increase. Right, this will want to increase, while if Q is way bigger than K, it would want to decrease. So this is what we are looking out for. So if we understand this, alright, we can actually apply to our idea of IP versus KSP. So let's write out a very quick equation of AgNO3, right, dissolving to form AgCl, right, dissolving to form Ag plus aqueous plus Cl minus aqueous. So basically, for us to form the IP or KSP expression, we will just write KSP is equal to Ag plus multiplied by Cl minus, and IP is equal to Ag plus times Cl minus. So notice this is the same as both of them have the same equations. And so what happens if IP is greater than KSP? So what will happen is that at that instant, alright, IP will want to decrease such that it is equal to KSP. So this is the eventual goal. So IP will want to become KSP. So how would we do that? If you look at this equation, alright, for us to decrease the value of IP, there's only one thing to do, which is to decrease Ag plus and Cl minus. Right, so you can see to decrease these two, the position of equilibrium has to shift to the left hand side. Alright, so that is the main idea that we are looking for. Alright, the position of equilibrium shifts to the left hand side. So this is the first thing that we will realize. When it's bigger, it will shift to the left, therefore it leads to precipitation. And of course, this is not the best way to describe this, because before it first precipitates, there will not be an equilibrium. So basically the idea is, as long as IP crosses KSP, you will get precipitation, and it will eventually dissolve. Alright, more of this Ag plus and Cl minus will crash out of the solution. It will precipitate out until IP is equal to KSP. So as long as you have a solid and a solution at equilibrium, IP is always equal to KSP, but momentarily, alright, IP might be greater than KSP, then you will get more precipitation. But before I get to that, let me just discuss a little bit more about IP versus KSP first. So like we mentioned, IP is equal to KSP is at equilibrium. This is what every system strives to be. But let's consider this unique case of IP is smaller than KSP. So when we have Q is smaller than K, the reaction will shift in a way where Q is going to increase such that it becomes the same as K. But in this case, since we do not have any AgCl solid when we are doing the precipitation process, all the ions are still dissolved in the solution. IP smaller than KSP, there's no way for it to increase, because the lack of a solid means that there's nothing to dissolve. Okay, so usually what we say is, when IP is smaller than KSP, no PPT. Alright, basically no precipitation at all. But once IP is greater than KSP, you will see PPT forming, and it will shift, the position of equilibrium will shift all the way till IP is the same as KSP. So let's take a look at the two common examples that we see. So the first kind of example is where we have a solution of, let's say, Cl minus, alright, and we add in aqueous AgNO3. So NO3 minus basically is just to make this salt soluble, and so when I'm adding Ag plus into this solution, and what happens is that as I add in drop by drop, alright, the IP of this, basically these two values, this Cl minus is fixed, alright, this is a fixed value, okay, but Ag plus will keep increasing until IP crosses KSP. Right, so at that point in time, we will start seeing precipitation. So that is why when we talk about precipitation, we are only interested in IP versus KSP. Okay, but once we cross the IP versus KSP point, when there's precipitation, now every bit of Cl minus that's added in, every bit of Ag plus that's added in, okay, some of them will will actually be left in the solution, and some of them will actually go out as silver chloride, as the PPT. So as we know, in the chapter of equilibrium, we have learned that when we introduce a stress to a system, the system will try to reduce that stress, but it will not eliminate it. So let's say I increase this by 2 units, maybe 1 unit stays in the solution, another unit participates in the shifting of the position of equilibrium to give you this AgCl solid. Okay, so this is something that's quite important. Then another way to look at it is where we take a spatula and with some soluble salt, and we keep adding bit by bit by bit. So let's say this is the KSP value. All right, the IP will constantly shift until this point, right, where it's larger than KSP, it overshoots the point, and some PPT will start coming out, and then it will start to decrease again until it reaches IP is equal to KSP, which is at equilibrium. Okay, so this is quite complicated. It is not as easy as you might hope it would be, but at the end of the day, what we are interested in is IP must be larger than KSP before precipitation takes place. IP smaller than KSP means no precipitation will take place, but when IP goes above KSP, there will be precipitation, and as a result of precipitation, it will decrease all the way till it reaches IP equals to KSP. And whenever we add additional salt into this solution, additional Ag plus, alright, it is actually consumed. Part of it is consumed, but part of it stays in the solution. This last portion is very, very important. Alright, this will be very important in the next video, where we will talk about precipitation with 2 different anions in the system.